You're listening to DTFHN from March 17th, 2026. I'm your open source and a trench coat host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who build things argue with people who critique things. Today's got that garage workshop energy where everything smells like solder and spite. Let's get into it. One of the top comments on this thread isn't even about Kagi Small Web. It's someone saying they've been using Kagi Search for months and they're not impressed. And that's actually the perfect frame for understanding why this project matters. Because Kagi Small Web isn't really a search product. It's an editorial act. Here's what it is: a curated list of personal blogs and small websites, maintained as a plain text file in a public GitHub repo. When you hit Next Post, it pulls from sites updated in the last 7 days. That's it. No algorithm. No engagement optimization. No feed ranked by predicted click-through rate. A text file and a 7-day window. The comments that matter are the ones from people who clicked the button and found something. One person landed on a post about building your own static site generator and loved it. Another commenter, who runs minifeed.net, a manually curated collection of personal blogs with valid RSS feeds, recognized it immediately as a kindred project. These are people who've been doing this work quietly, maintaining lists, checking feeds, verifying that humans wrote the words. The small web has always existed. What's new is a search company pointing at it. Now apply the architecture test. The index is a text file on GitHub. Anyone can submit. Anyone can fork it. Anyone can see exactly which sites are included and why. If Kagi changes direction tomorrow, the list survives. Compare that to how discovery works on every major platform. Proprietary ranking, opaque signals, content valued by its ability to generate engagement rather than its quality. Those systems aren't broken. They're working exactly as designed. They're just designed for someone else's objective function. The clinical observation is this: Kagi took what could have been a proprietary differentiator, a curated index of quality small websites, and published it as open source. The smallweb.txt file is the product. The search integration is a distribution channel. That means even the commenters who aren't impressed with Kagi's search results can still benefit from the curation work. There's a request in the comments for language filtering. Someone pointing out that the small web exists in more languages than English. That's the kind of feedback that makes open source work. It's not a complaint filed into a support ticket. It's a feature gap identified in public, attached to a repo anyone can contribute to. The small web never went away. People kept writing. The infrastructure just stopped surfacing them. What Kagi did here is less invention than recognition. Pointing a searchlight at what was already there, and critically letting everyone see where the light is aimed. We talked about Kagi pointing searchlights. Well, they're also pointing translation engines in a truly unhinged direction. In 1980, Josef Weizenbaum built ELIZA at MIT, a program that could pass as a Rogerian therapist by reflecting your own words back at you with a few structural transformations. No understanding, no meaning, just pattern matching that sounded like empathy. Weizenbaum was horrified when people started treating it as real. He spent the rest of his career warning that humans will project depth onto any sufficiently polished surface. 60 years later, Kagi built a translator for LinkedIn Speak, and the results are so accurate, it's unsettling. The tool takes normal human language and transforms it into the peculiar dialect that dominates professional social media. That frictionless, relentlessly optimistic, growth mindset prose where nobody gets fired. They transition to their next chapter. Where nobody cleans toilets, they deliver operational excellence in hygiene infrastructure at a Tier 1 technology company. The engineering achievement here is that the output is indistinguishable from the real thing, which tells you something profound about how formulaic corporate communication actually is. It's Eliza in reverse. Instead of a machine pretending to be human, it's exposing how humans pretend to be machines. The community stress tested it beautifully. Someone fed in the Navy SEAL copy pasta and got back a perfectly coherent LinkedIn post about high-impact career results and cross-functional warfare operations. Someone input 5,000 repetitions of a single profanity and received a post about scaling output by 10,000% through relentless grit. The Gangsta's Paradise lyrics became a reflection on navigating non-traditional career pathways. Every transformation landed because LinkedIn Speak has such rigid structural rules that you can formalize them into a translation layer. That's not just comedy. That's computational linguistics doing real work. Pull this thread and you find something Kagi keeps doing well. They build tools that make you think differently about the systems you already use. Small Web resurfaces the independent internet. Orion gives you a WebKit browser without the Safari lock-in. And now a joke translator that doubles as genuine criticism of how platform incentives flatten human expression into engagement-optimized paste. The tool is free. It's on their public site. Anyone can use it. That matters because satire works best when everyone has access to the punchline. Not just the people who already see through the performance. Every LinkedIn post you read after using this thing will sound slightly different to you. You'll hear the pattern matching. You'll notice the Eliza underneath. Weissenbaum warned us that polished surfaces fool people. Kagi just handed everyone away to see the seams. Moving on. I spent a massive hours once debugging a pipeline where a single unescaped space in a file name brought down an entire deployment. And the whole time I kept thinking, I use this thing 8 hours a day and I've never once looked inside it. The shell is like plumbing. You only think about it when sewage backs up into your kitchen. Andrew Healy apparently had the same realization, except instead of cursing at his terminal, he woke up 3 hours before his family, brewed a pot of filter coffee, and just built one from scratch in C. And the thing that makes this worth talking about is how clarifying the exercise turns out to be. Building a shell is like disassembling a clock. A clock every day. You know what it does, but the moment you lay out the gears on a table, you realize you had no idea why the minute hand moves the way it does. Fork, exec. Wait, 3 system calls and you've got a running command. His shell, called onJack, starts as a read-eval print loop, grows a tokenizer that splits on whitespace, learns to expand environment variables, handles pipes by daisy-chaining file descriptors between child processes, tab completion, command history. The whole arc from I can run ls to I can run printf, abc pipe, tria pipe rev, and get CBA back happens in one sitting. The comments on this are worth reading because they immediately split into 2 camps. One group says building a shell is a great exercise, but string parsing robs 2/3 of the joy. The other group, and they're right, says the corner cases are the point. Every escape character, every quoting rule you stumble into, teaches you something about how the operating system actually works underneath. This is what I call a bootstrap artifact. Healy published the code. It's on GitHub. Anyone can read it, fork it, extend it. A working shell implementation, small enough to hold in your head. Written by someone who bothered to explain every decision along the way. That's not a tutorial. That's a ladder left in place for the next person. The best part? He ran out of coffee before he ran out of ideas. Tab completion works, history works, pipes work, signal handling works. The thing he built in a morning, before anyone else woke up, demystifies a tool that most developers treat as a black box for their entire careers. The code is right there. Go read it. Better yet, go break it. That's where the real understanding starts. Move on. December 18th, 2024. That's when the Digital Childhood Alliance launched. Days later, it was testifying before the Utah State Legislature on SB 142. An organization that didn't exist the week before Christmas was shaping law before New Year's. Follow that detail, and the whole architecture reveals itself. A Reddit researcher, working under the handle UpperUp, traced over $2 billion flowing from Meta through a lattice of non-profit shells spanning 45 states. The strategy is elegant in the worst possible way. Fragment spending across enough entities that FEC disclosure requirements never trigger. $70 million through super PACs alone, structured specifically to stay beneath transparency thresholds. Not a bug, a feature. Now take Meta's stated principle to its logical end. They say this is about child safety. Fine, run it forward. The proposed laws mandate something called a Get Age Category API, baked directly into the operating system. Every app on your phone can query it. That's not age verification. That's a persistent identity layer fused into the device itself. Your phone would know who you are at the kernel level, all the time, for every application. And here's the part worth sitting with. Meta's own platforms would be exempt. The bills target app stores. Apple and Google. Not social media. Meta already built this infrastructure into Horizon OS for Quest. They want their competitors forced to build the same surveillance plumbing, under legal mandate, while Meta's core business walks untouched. It's the equivalent of an oil company lobbying for emissions regulations that only apply to electric vehicles. Meanwhile, Europe's EDAS 2.0 uses zero-knowledge proofs. You prove you're over 18 without revealing your name, your birthday, anything. It's open source. It's self-hostable. Small projects and free software are explicitly exempt. 2 continents. 2 completely different answers to the same question. And the architectures tell you everything about the intent. The real threat runs deeper than Meta. If these bills pass, every Linux distribution, every privacy-focused Android fork, every custom ROM would face a choice. Implement government-mandated identity verification, or become illegal. The open computing stack, the entire ecosystem that lets you own your own device, gets caught in the blast radius of a competitive lobbying play dressed up as protecting kids. The investigation is public. The funding trails are documented. Go read it. So who's actually building the future instead of lobbying against it? Story 5. Grace Hopper's Revenge. I need permission to fetch the full article. The pace cuts off mid-sentence. Let me work with what's here and write the segment. What does it actually mean for a programming language to be readable? And readable by whom? For 50 years, we've assumed the answer was human programmers. We designed languages to be parsed by people, debugged by people, reasoned about by people. Kernine's law became gospel. Keep it simple. Write code a human can hold in their head. And that was right, because humans were the only ones reading it. But the autocode bench results flipped that assumption on its head. across 20 programming languages and multiple models. The languages I handles best aren't the ones with the most training data. Python and JavaScript, the two languages drowning in examples and tutorials and Stack Overflow answers, sit near the bottom. At the top, Elixir, Racket, Kotlin, C#. Languages with clear structure, strong type systems, functional paradigms. Let me play devil's advocate for a moment. Maybe this is just a data quality argument. Maybe Python and JavaScript have so much bad code in the training set that the signal gets buried in noise. The comments on this piece raise exactly that point, and it's fair. But even if you grant that, even if messy training data explains some of the gap, you're still left with the uncomfortable implication that the most popular languages in the world have accumulated so much cruft that machines can't reliably learn good patterns from them. That's not a defense. That's a diagnosis. The article draws an analogy to Tesla's bet on vision over LiDAR. Roads weren't designed for laser scanners. They were designed for human eyes. Painted lines, color-coded lights, signs shaped like their meanings, build for the existing interface, and decades of infrastructure come free. The same logic applies to code. If AI is now the primary reader of code, the entity that has to parse intent, maintain context, and generate correct implementations, then the load-bearing interface isn't syntax, it's semantics. How plainly does a language express what a program means? Grace Hopper understood this in Minthing COBOL 5 config. She built COBOL because she believed programming should read like English, that the specification was the program. The industry spent decades mocking COBOL for being verbose and unsophisticated. Now we're arriving at exactly her thesis from the opposite direction. Machines that think in language, working best with languages that think clearly. The languages that will matter most in an AI-driven world aren't the ones with the biggest ecosystems. They're the ones where structure carries meaning, where the architecture of the code itself communicates intent. The tools exist. The question is whether we optimize for the habits we have or the capabilities we're gaining. Moving on. Let me be honest about something. If you're building mission-critical software or pushing the boundaries of formal mathematics, you probably should just use Claude Opus. It scores 39.6 on Mistral's own benchmark. Leanstral tops out at 31.9. That's not a rounding error. That's a meaningful gap in capability. And if correctness is what you're after, if you're formally proving that your code does what it claims to do, you want the best tool available. Case closed, right? Except look at the price column. Opus costs $1,650 to run that benchmark. Leanstral costs $290 at its highest setting, at its lowest $18. That's not a cost difference. That's the difference between a tool that exists for funded research labs and a tool that exists for everyone else. And everyone else includes the graduate student trying to formalize a proof for her thesis, the startup that needs verified code but can't justify burning through thousands of dollars in API calls, the independent researcher in Nairobi or Bangalore who has the mathematical talent but not the compute budget. The question nobody's asking is this: what happens to formal verification as a field if only 3 organizations on Earth can afford to do it well? Because that's where we've been heading. Formal proof engineering has been trapped in this paradox, where the tools that make it accessible require expertise that makes it exclusive. Lean 4 cracked the language side of that problem. It's expressive enough to describe everything from perfectoid spaces to Rust memory safety properties. But having a beautiful proof language doesn't help if the agent that drives it costs more than your monthly cloud bill. Leanstral runs on 6 billion active parameters. 6 billion! It's a sparse mixture of experts model that punches absurdly above its weight class because it was trained specifically for this domain instead of trying to be good at everything. One of the Hacker News commenters nailed the irony. Yes, Opus is better, and yes, Opus costs 6 times more, and somehow they think that settles the argument in Opus's favor. As if the history of technology isn't littered with superior products that lost to good enough alternatives that were actually available to people. A PATI 2.0 license. Weights you can download. A free API endpoint. This is bootstrapism. Put the tools where people can reach them and watch what happens when formal verification stops being a luxury. So what happens when you hand people the tools and say, go build whatever you want? Sometimes they build something nobody expected. Voxel destruction is a bandwidth problem disguised as a physics problem. Every block you blow up in Teardown changes the world's state. In single player, that's fine. The simulation just marches forward, but the moment you add a second machine, every changed voxel becomes data that needs to cross a network. And Teardown's world is made of millions of voxels. Blow up a building, and you've just generated a diff the size of a small database migration. The team at Tuxedo Labs knew this in 2021 when they first tried the obvious approach. Just send the voxel changes as they happen. It choked the connection instantly on any large destruction event. Meanwhile, a community project called TDMP managed rudimentary multiplayer through reverse engineering and DLL injection, yet mostly synced player positions and inputs. And because the engine isn't deterministic, worlds would quietly diverge. You'd be standing in a building your friend had already demolished. The solution they landed on is elegant in that quiet engineering way, where the cleverness is in what you don't send. Destruction commands are made deterministic, instead of transmitting the resulting voxel changes, which scale with the size of the objet. You transmit the operation that caused them, cut hole at coordinate XYZ, reassign this shape, reconnect this joint. The commands are tiny and identical, regardless of whether you're chipping a brick or leveling a warehouse. As long as every client applies them in the same order, the worlds stay in sync. This required rewriting the destruction logic in fixed-point integer math to dodge floating-point non-determinism across different machines. The conventional wisdom has long held that floating-point is unsafe for deterministic simulation, and the Teardown developer notes that this is more nuanced than people think. A topic he promises to write about separately, which frankly might be more valuable than the multiplayer feature itself. Everything structural rides a reliable order to stream. Everything cosmetic. Positions, velocities, transforms. Uses eventual consistency on an unreliable channel. 2 parallel streams, 2 different consistency guarantees, matched precisely to what each type of data actually requires. No dedicated servers. The host is the server. The whole thing shipped as a free update to the existing game. Millions of voxels, synchronized destruction, and they just patched it in. Remember that Viktor A tool we mentioned earlier? Someone decided waiting for official access wasn't the move and open-sourced the whole thing. I'm unable to fetch the article. Permission for web fetch keeps getting blocked. I only have the title, Reverse Engineering Viktor, and making it open source. The URL, and these comment fragments to work from the comments, I can piece together. Viktor appears to be a commercial product that launched something similar to OpenClaw for Slack. Claw is MIT licensed, suggesting Viktor may have built a proprietary product on top of open source code. There are legal takedown concerns. Someone mentions it's connected to someone, PJ Outa Dubai. The comments hint this is about a company taking MIT licensed open source, possibly related to Claude Claw, repackaging it as a proprietary Slack product. and someone reverse engineering it back to open source. Do you want to? 1. Grant web fetch permission so I can get the full article and write an accurate script. 2. Have me write based on what I can infer from these fragments. Risky. I might get details wrong. Now, from who owns the code to who ships the code. Let's talk about what CI actually looks like when your whole company fits in one room. I have enough from the article text and comments to write this. Let me craft the segment. One commenter nailed it in 5 words. Quote, Jesus, this is why Bezo was invented. That's the top reaction to PostHog publishing their CI numbers. And honestly, it's hard to argue. 575,000 jobs in a single week. 1.18 billion log lines. 33 million test executions. 3.6 years of compute time. Burned in the 7 days by 100 people. Run this forward. Imagine you're an engineer at PostHog on a Tuesday. Their busiest day. Where 300 days of compute get chewed through in 24 hours. You push commit, 221 parallel jobs spin up. Your test pass. Great. Except somewhere in that sprawl. A test that passes 95% of the time just failed for the 4th time today. And 3 of your colleagues are independently staring at the same red bill, each wondering if they broke something. This is the article where Mendril, a startup founded by former Docker engineers, reveals what CI looks like when a fast-moving team actually measures it. And the numbers are fascinating precisely because PostHog is doing everything right. 99.98% pass rate across 22,000 unique tests. That's genuinely excellent. But at 33 million weekly executions, that tiny failure rate still generates enough noise to become a productivity tax on the entire org. Now, the comment section is doing exactly what you'd expect. One reader got what they called slop nausea from the writing style. Too many, it's not X, it's Y constructions. Fair. Another pointed out that a 99.98% pass rate isn't actually good enough. That the only acceptable rate is 100% and quarantining flaky tests is just sweeping the problem under the rug. That's the purest position, and in a vacuum, it's correct. But the pragmatist position is that when you're merging 65 commits to main per day with 98 active contributors, you need triage now and root cause fixes later. The interesting question buried in all of this isn't whether Mendril's AI agent can diagnose flaky tests. It's what happens when AI coding tools are generating the PRs that feed this pipeline. The Mendril founders built Docker's CI a decade ago and say the problem has only gotten worse since. Imagine this, forward 5 years. AI agents writing code, submitting pull requests, triggering CI runs, and then another AI agent diagnosing the failures and opening fix PRs. Agents debugging agents in a loop, with humans occasionally glancing at dashboards. PostHog's repo is public. Their CI is public. Their numbers are public. That matters. Because the next team hitting these scaling walls doesn't have to guess. They can look at real data from a real org and calibrate accordingly. The tools exist. The data is available. Whether you was Mendril or Bezel or something else entirely, the first step is the same. Measure the problem honestly, then decide what the noise is actually costing you. Measuring your infrastructure honestly is step 1. Step 2 is making sure the allocator underneath it all isn't quietly wasting everything you optimized. In Yuan Jiao Doufan, the Apache web server held 60% off the internet. It wasn't the fastest. It wasn't the most elegant, but it was there, it was open. And the people who depended on it could fix it when it broke. Then something quietly dangerous happened. The companies building on Apache started treating it like a utility. They took more than they gave back. The foundation software that held up their entire business got neglected precisely because it was so reliable that nobody thought about it until something went wrong. Jemalloc has lived that exact arc. For years it's been one of those invisible load-bearing walls in modern infrastructure. Every time your phone pulls a feed, every time a recommendation engine scores a candidate, every time a cache layer decides what stays and what gets evicted. Somewhere underneath, a memory allocator is making thousands of decisions per second about how to carve up your RAM. Jemalloc does this extraordinarily well. It's one of the most carefully engineered pieces of systems software in production anywhere. Handling fragmentation and huge pages in cache locality with a craft that most application developers never need to think about. That's the point. You're not supposed to think about it. It just works. Until it doesn't. Last June, the Jemalloc repositories got archived. The project's founder, Jason Evans, had effectively stepped back. Meta, the primary steward, had accumulated technical debt by chasing short-term optimizations that violated the allocator's core design principles. The community noticed. The feedback was pointed. What's worth paying attention to here isn't the apology. It's the unarchiving. Meta went back to Jason Evans, acknowledged what went wrong, and got the original repository restored. They're now committing to huge page allocator improvements, ARM64 optimization, and, critically, cleaning up the mess they made. One commenter who worked on kernel patches for Gemalloc's purging mechanisms at Facebook noted that this kind of deep infrastructure work was never popular internally. That tension between what's popular and what's load-bearing is the whole story. The roadmap is public. The repository is public. The post-mortem conversation happened in public. This is what good stewardship recovery looks like. Not a press release, but an unarchived repo and a list of concrete technical commitments that anyone can track. Memory allocation isn't glamorous, but every byte of efficiency at this layer compounds across billions of requests. The foundation work matters most precisely when nobody's watching. This has been your daily tech feed for Hacker News for March 17, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that matters to you. We'll see you back here tomorrow.